Okay, ladies and gentlemen, let's talk about changes of state. Changes of state are when a substance goes from its solid to liquid to gas form. All of those, or vice versa, if it goes from gas back to liquid, back to solid. They're all physical changes. The stuff is the same stuff, just happens to be arranged a little differently at the submicroscopic level. Has to deal with what we call energy and the kinetic molecular theory, which we will get to later in the year. On the table right now we have water. We have water boiling. In order for water to boil, of course, it needs to be at a certain temperature. It needs to be at or exceed a certain temperature. We call that the boiling point, when you heat water so much that it'll begin to boil. So right now, we're not at that boiling point. We don't have enough heat. But if I put it back on the hot plate, give it a minute, and that water will warm up and reach that critical temperature. That's when the water, the liquid level, breaks free and becomes a gas. It goes to we call it water vapor. We've reached what we call the boiling point. And the water will sit there and boil away until it's all gone. Point is, that's liquid water, and this steam is the gas form of water. It's all water. As a matter of fact, I can get that water back if you, what we call, condense it. So if you take a liquid and go to the gas, we boil it or vaporize it. We've gone beyond the boiling point. If we take that gas and we bring it back to a liquid, which you probably experience when you have grab a shower, the bathroom mirror fogs up because all that water vapor collects on the mirror. Well, that's condensation. You've reached the point of condensation. You're going back from gas to liquid. That boiling point and condensation point, they both refer to a specific temperature for that material. For water, water boils at 100 degrees Celsius. Water condenses at 100 degrees Celsius. It really is just a discussion of which way you're going. Are you going from liquid to gas? You're boiling it, you're adding heat. Or you're going from gas to liquid. You're condensing, you're removing heat. In either case, you cross that threshold of 100 degrees. Same thing for water at the solid state and going to liquid state, or vice versa. Here we have old-fashioned ice cube tray. Got a bunch of ice cubes. Matter of fact, some of these ice cubes, when I put it in the freezer, didn't even freeze all the way. And you can see in there a trapped air bubble in that ice cube. That means there is some liquid water trapped in this solid water. We call solid water ice. In order for this water to have frozen, it had to reach the freezing point, which we know is 0 degrees Celsius. Or in order for ice to melt, it has to go and get warmer than the freezing point. We call that the melting point. Again, it's just the direction you're going. If I put that ice cube, I'm gonna put this little ring around it so it doesn't slide around. I can watch it sit there and melt quite readily on this little plate that I have here. And so that solid getting warmed up higher than 0 degrees Celsius starts to melt and become liquid. So any substance can go through these changes. It just depends on the substance at what temperatures these things happen. A chunk of metal is solid. In order to melt it, you'd have to get to a decently high temperature, hundreds of degrees Celsius. And then if you were to boil a metal, which it could do theoretically, you'd have to go to even a higher temperature. And then of course the reverse. If you took gaseous metal, which is very difficult to think about, and were to cool it to the condensation point, it would go back to liquid. And then that liquid eventually would, if you continue to cool it past the freezing point, would turn to solid. The book that we use mentions salt, and salt, a lot of generic what we call salts have very high boiling points, melting points, because most salts are a solid at room temperature, and you need to get them to a liquid. It takes a lot of heat to do that, and I can only imagine trying to get them to a gas. But also realize the air around you is already in gas form. And the air around you could be cooled and condensed to a liquid nitrogen. What do you know about liquid nitrogen? Most of the air is comprised of nitrogen, and yes, we can compress it to a liquid. It's really cold. We'd have to take air and really, really, really cool it to get to that condensation point. And then even beyond that, could we freeze nitrogen to a solid? That would require a really, really, really cold environment, and there's a couple other tricks we can do to make that happen. But we'll learn about those later. I'm going to take a break, clean this up, and then we'll talk quickly about the difference. We'll talk about the difference between vaporization and boiling, and vaporization versus evaporation. So give me a moment, and I'll be right back. So one of the other things we have to make mention of is evaporation. Evaporation is a change of state, but you don't really have to go past any kind of boiling point to do it. Boiling point really refers to adding enough heat where all of the sample of your liquid is going to all try to turn into gas kind of at the same time. Whereas evaporation, your materials do change to gas, but only small percent of the overall sample tries to escape as gas, and there's reasons why. And again, we'll learn about those later in the kinetic molecular theory chapter. But there is a term called volatility regarding evaporation. If something is more volatile, it tends to evaporate much more readily than materials that are not volatile. So I have two samples here. I have water, and I'll take a couple drops. We'll do like 1, 2, 3, 4, 5. Sure, 5 drops of water. And I have a sample of what we call hexanes, which is an organic solvent. And we'll do 1, 2, 3, 4, 5. Now we can already tell there's something very different about this, by the way water beads up the way it does versus the way this did, okay? And the evaporation is happening already. Now you can't smell it like I can, but these hexanes are evaporating. And I'm going to turn on a fan. It's slightly off camera here. Turn it on low. And we'll let these evaporate. So they're under the same conditions of wind. And you can see the hexanes are evaporating quite readily. The hexanes they're volatile. They evaporate quickly. Water is not volatile. Water does not evaporate quickly. Now this is a physical change. It's just the materials going from liquid state to gas state, but not as in a quick manner as boiling. A lot of people hear the term volatile and they think something along like it's very explosive, you know, and you hear that in everyday language, like, well, the situation overseas with this country is volatile. So it gives that notion of fiery and explosion and such. Well, technically volatile or volatility isn't directly related to something exploding, by the way. This is all gone, the water's still here. I'm gonna turn the fan off. But the reason that phrase and meaning comes about is because a lot of the times when materials are in fact volatile, they also happen to be or can be flammable. Because they evaporate so readily, because of their nature, they're usually quite flammable. So the volatility translates into fiery and explosion when really they're two separate things. Okay, so I hope that helps.